Welcome back to the Data Dynamics podcast. Today, we're diving into the fascinating realm of multi-leader replication in databases. If you've ever wondered how data stays consistent across different locations, or how systems deal with conflicts when multiple users try to update the same record, you're in for a treat. We'll unpack the challenges of conflict resolution, the strategies used to maintain data integrity, and the technologies that are shaping the future of replication. So grab your headphones and let's jump right in. To start, let's clarify what multi-leader replication actually means. In a traditional database setup, a single leader node manages all write requests, ensuring that data remains consistent. However, in a multi-leader environment, several nodes can accept writes at the same time. This approach can boost performance and availability, but it also opens the door to potential conflicts, especially when different leaders receive concurrent writes for the same record. One common strategy to minimize conflicts is to route all requests from a specific user to their designated leader in a particular data center. This setup creates the illusion of a single leader environment from the user's perspective. But what happens if a data center fails or a user moves closer to a different data center? Suddenly, the conflict avoidance strategy can falter, leading us to the possibility of simultaneous writes on different leaders. So, what exactly does a conflict look like? Picture two leaders trying to update the same field in a record at the same time. For instance, if leader 1 updates the title to B and then to C, while leader 2 updates it first to C and then to B, we end up with an inconsistent state. Leader 1 sees the final value as C, while leader 2 sees it as B. Clearly, this inconsistency is not acceptable. We need a reliable method to ensure that all replicas arrive at the same final value. To tackle these conflicts, several strategies can be employed. One popular method is last write wins, or LWW, where each write is assigned a unique ID, such as a timestamp or a UUID. The write with the highest ID is deemed the winner. While this method is straightforward, it can result in data loss, as earlier writes may be discarded. Another approach is replica priority, where each replica has a unique ID. Allowing writes from higher-numbered replicas to take precedence, this method can also lead to data loss. Alternatively, we could consider merging values. Instead of discarding conflicting writes, we can merge them. So, if two titles are B and C, the merged result might be BC. This approach preserves more information but can introduce ambiguity. Another option is explicit conflict recording, where conflicts are logged in a dedicated structure and resolved later, possibly with user input. For example, CouchDB allows applications to handle conflicts by returning multiple data versions for resolution. Most multi-leader replication systems give developers the flexibility to implement their own conflict resolution logic. This logic can run during writes or reads, but it typically needs to execute quickly and cannot rely on real-time user input. However, it's crucial to recognize that not all conflicts are as simple as two writes competing for the same field. Take, for instance, a meeting room booking system where two groups attempt to book the same room at the same time. Even if both bookings check availability, a conflict can arise if they are processed by different leaders. This scenario underscores the necessity for robust conflict detection and resolution strategies. Now let's explore some innovative approaches to conflict resolution that are gaining traction. One exciting development is conflict-free replicated data types, or CRDTs. These data structures allow multiple users to edit concurrently while automatically resolving conflicts in logical ways, and they've been implemented in databases like React 2.0. Another approach is mergeable persistent data structures, which track historical changes and utilize a three-way merge function, much like how Git handles version control. Then there's operational transformation, the algorithm behind collaborative editing tools like Google Docs. which enables multiple users to edit a document simultaneously without conflicts. As we delve into the mechanics of data replication in a multi-leader setup, it's essential to understand how data is propagated to maintain consistency. When a write occurs, it must be sent to all other leaders, requiring a well-defined topology for data flow. For example, in an all-to-all topology, every leader communicates with every other leader, enhancing fault tolerance, but potentially leading to issues like out-of-order writes if network conditions fluctuate. On the other hand, more restricted topologies, such as circular or star configurations, can be more efficient but may present single points of failure. If one node goes down, it can disrupt communication between others, complicating recovery. Another critical challenge is maintaining the causal ordering of writes. Imagine if Leader 1 processes an insert before an update, but Leader 2 receives them in the opposite order. This discrepancy can lead to inconsistencies. Simply timestamping writes isn't sufficient, as clocks may not be perfectly synchronized across nodes. As we wrap up our discussion, it's important to remember that the replication strategies we've explored, both single-leader and multi-leader, are designed to ensure data consistency and availability. Yet, they come with trade-offs, particularly in how they handle conflicts. In conclusion, multi-leader replication presents exciting opportunities to enhance database performance and availability. But it also brings complex challenges, especially regarding conflict resolution. As we continue to explore these technologies, it's clear that the future of data synchronization will likely involve more sophisticated algorithms and structures that can automatically resolve conflicts, ultimately making life easier for developers and users alike. Thank you for tuning in to this episode of the Data Dynamics Podcast. We hope you found our exploration of multi-leader replication insightful. If you have any questions or topics you'd like us to cover in future episodes, don't hesitate to reach out. Until next time, keep exploring the fascinating world of data.